Okay, so when is a function differentiable? So in the past like 3 or 4 lessons, we talk about a couple of things. Okay, it is defined, limit, and then that bring to continuous, and the last thing we'll talk about is differentiable. Well, differentiability, okay, I'll just say differentiable or not. So that's the stage, okay? So define a limit that not affecting each other, so can be both exist or both not exist, or one exists, one not. And then if both satisfied, okay, we have defined, we have limit, but if they are equal, then it's continuous. If it's not equal, it's not continuous. And the next stage we'll talk about is differentiability. So whether the function is differentiable or not. There's a lot of things I need to emphasize in this exercise. If it's continuous, it first needs to be continuous, and then we think about whether it's differentiable or not. If it's not continuous already, then we just not think about differentiability at all. Okay, so the function is satisfied, is connected together first, and then we start to talk about at that point whether it's differentiable or not. So let's have a look. A function f is said to be differentiable at x equals to a if that exists. Okay, if that exists. What's that? That's f dash a. Okay, the notation is f dash a. So if it's f dash a exists here, then we say it's differentiable, but it's not that helpful. Okay, this formula is not basically used to test whether it's differentiable or not. It's the theory. Okay, it's the theory. So in general, a function is not differentiable at x equals to a if the graph is not continuous at a. Okay, that's the first thing. If it's not continuous at x equals to a, then we're not talking about anything else. Okay, we stop there. So when it's not continuous, so when there's a vertical jump, like a graph like that, okay, that's a vertical jump. When there's a horizontal jump, so what is a horizontal jump? That's a horizontal jump. In between those 2 points, there's no value given. Okay, that's a horizontal jump. And then there's a vertical tangent. Vertical tangent. So let's say we have a graph looks like that. The truncus at x equals to 0. That's a vertical jump there. Palace photo. Okay, a vertical jump here. A vertical tangent that's not continuous as well as at x equals to 0. And then that's the first thing. Okay, that's number 1, when it's not continuous. Okay, the second one that's not differentiable has a sharp point, okay, or cusp at x equals to a. So what is a sharp point? A sharp point is like a tick. Okay, this point is called a sharp point. It's just suddenly change direction. It's going towards there first, and then suddenly change to the other direction. That is called a sharp point. Okay, so this is not differentiable. Okay, I'll tell you why it's not differentiable later, but like that's one type which is not differentiable. Okay, number 3. Okay, number 3 is this one. Derivatives never exist at endpoints, regardless whether the endpoints are included or excluded in the original function. Okay, that's a part like students always forget. Okay, endpoints never have derivatives. Even though you can derive the function, even though you can substitute the values in, but it's not exist for the endpoints, regardless whether it's defined or not defined on the original one. So let's have a look. This function is not differentiable here. It's not differentiable here, regardless whether it's defined or not defined, because that's the endpoints. Endpoints will not have derivative. So let's say the derivative here is the original function is -2, and that is 4. Okay, -2 to 4. If I'm asking you where the function is differentiable, you will only say it's from -2 to 4, open bracket on each side. When the function is differentiable, it's from -2 to 4, open bracket, because you won't include any endpoints. Okay, so that's open circle, -2 to 4. Okay, so Let's have a look at the next line. Function can be joined if they intersect. Okay. Function can be joined if they intersect. Just like an open circle and a closed circle, they have same x, same y value, is joined together. Okay, it's continuous. That's the continuous definition. Do you remember when we do the continuity part, we try to think which function is continuous, and we try the connection points. Like 3 is the connection points, then we try the connection points, whether they have the same y value, and then we say it's continuous or not. So if they have the same x, same y value for one closed circle, one open circle, it is connected and it is continuous, but it's not necessary to be differentiable. So when it can be differentiable, okay, function can be joined if they intersect, but they can only join smoothly. They can join smoothly or not smoothly. So what is smooth? What is not smooth? So give you an example here. So this graph. Let's say that's two functions. Okay, that's f1x, that's f2x. They join at this point. It is quite smooth. Okay, just by visually look at it, it's quite smooth. Well, later I'm not asking you to visually see it. Okay, there's a function we tested, but like now you just look at this point. It's quite smooth. It's connected quite smoothly here. Perfect connection. But let's see this one. Can you see that's not perfectly connect? Like it's not smooth. It's not smooth. This is kind of sharp point already. It's not smooth at all. So that is, they both joined at that point. Okay, they both joined at that time. It's joined together for this point and this point. But for the first graph, it's joined smoothly because like the curve is perfect, like smooth. You can see it. But the second one, it's not. Okay, just like that. It's not joined smoothly. So if you want to say what is joined smoothly, what's the formula for joined smoothly? How I can know it's joined smoothly or not? Is this following thing here. Let's say fx is given by two separate functions, okay, and connect at the point A. Connect at point A. So I have f1x and f2x. They connect at point A. So if f1a equals f2a, that's joined together, okay? This gives you joined together. Why is joined together? Because they have the same y value at the same x value. One open circle, one closed circle. They join together. But the join smoothly is this here. Well, f1-a equals f2-a. On two separate functions, the gradient at the same point will be the same. Well, what is joined smoothly? Is the curve follow the same like pathway? It's like looks like really good. So that is the gradient. The gradient at the same point must be the same. Then you will connect smoothly. Okay, the trend is the same. I'm going that way as well for two different separate graphs. So that is joined smoothly. Is the derivative at two separate functions at a single point are the same. Okay, if this is the same, then it's joined smoothly. So first you need to satisfy it's joined together. Second, I need to satisfy is the gradient are the same. Then it's joined smoothly. So two conditions here. Okay, two conditions here. Well, if it's not joined smoothly, then I can't derive that point. If it's not joined smoothly, I can't derive that point. Why? Just have a think about this one. This graph I draw here. On the left-hand side is a decreasing linear, right? The gradient is negative. On the right-hand side, the linear is increasing, and I have a positive gradient. Which gradient you will take? Well, at the same point, this point is on this one and on the right-hand side. Which one you will take? Do you take the negative one or do you take the positive one? Oh, well, if you take one, why not the other? So you can't choose a value to take. So it's two separate gradients on a single point. Contradicts each other, so I can't take any. So it can't derive at that point. That point is without derivatives. Okay, that point is without derivatives. So that is joined smoothly. So if two curves join smoothly, first the curve intersects. Okay, that's this formula here, and the gradient at the contact point are the same for both functions. That's this function here. Okay, so one's gradient the same, one is y value is the same. Any questions so far? So what you need to think about is like two endpoints. Well, if the point is not continuous, do not think about whether it's like derivative define or not, this definitely can't derive if it's not continuous. Second, if you have endpoints, well, both endpoints or one endpoint definitely can't derive. Number 3 is you test any connection point. On that connection point, do you have the same gradient? Oh, well, first you need to test, do we have the same y value? Okay, if it's not same y value, it's not connected, it's not continuous. Back to situation number 1, not differentiable. Number 2 is they join together, but do you have the same gradient to join them? If they have the same gradient, yes, I can derive that point. If I don't have the same gradient, no, I can't derive that point. Okay, so that is the differentiability. So let's have a look at example 2 here. Okay, for example 2. Well, for example 2, half bracket here. Fx is 2 functions. One is x, one is negative x. Okay, so when x greater or equals to 0, we have x. When x is less than 0, is negative x. Can you just sketch this hybrid function for me? Okay, just sketch this hybrid function for me. Just somewhere on the left. Okay, so first of all, 0 is the connection point. Okay, 0 is the connection point, and there's no endpoints, and the graph is connected. So I will say f1x equals to x, f2x equals to negative x. So f10 equals to 0, f20 equals to 0 as well. That tells us is connected. So I will say it's continuous. Okay, it's continuous. So what's f1 dash x? f1 dash x is 1. f2 dash x is negative 1. So f1 dash 0 is not equals to f2 dash 0 because 1 is 1, 1 is negative 1. That's the sharp point. The derivatives are not the same. Okay, derivatives on the same point are not the same. So it's not differentiable. Is not differentiable at x equals to 0. All the other points is fine, just not that connection points. Okay, that connection points is not working well, so it's not differentiable at that point. Okay, it's not differentiable at that point. So sketch the graph of the derivative for a suitable domain. Let's sketch the graph of derivative. So on the right hand side, when x greater than 0, I will have 1. But at 0 it's not differentiable. So you will have open circle at 1 and open circle at negative 1 as well. The red one is dy dx. Well, I would say f dash x. The blue graph is the fx, but the red graph will be the dy dx. Because on the left hand side is negative 1. Okay, on the left hand side, the gradient is negative 1 everywhere. And on the right hand side is just 1. But at 0 it's 2 open circle because I can't take the derivative. You can see as well at the derivative graph, okay, at 0, 1 take 1, 1 take negative 1. How it can work? It doesn't work, okay? So that's why it's both open circle here. So that is the derivative function. So the differentiability will be, it can be derived for x belongs to 0 except, x belongs to R except 0. So it is differentiable at x belongs to R except 0. Just not differentiable at 0. All the other points is fine. Okay, all the other points is fine. Questions? Okay, that's an easy one because you can obviously see that's a sharp point. You know that can't be derived. Okay, that's really clear. Okay, let's have a look at question number 3. Okay, for the function with this rule x greater than 0 equals to 0 or that rule less than 0. So find f dash x and sketch the graph of f dash x. Okay, first of all, which point do you think that might be a problem? 0. Okay, it's the connection point. It's 0. That's the only connection point. So 0 might be the problem point. So I would say f1x equals to x squared plus 2x plus 1. f2x equals to 2x plus 1. Okay, f1 dash x equals to 2x plus 2. f2 dash x equals to 2. So 0 might be the problem point. I will say f1 0 is 1. f2 0 is 1 as well. They're the same point. So I will say is continuous. It's connected. Well, it's continuous first. If it's not continuous, I'm not going to do the next step because there's no point to talk about differentiability for an incontinuous question. But if it's continuous, I will say f dash 1 0 equals to 2. f dash 2 0 equals to 2 as well. So it is smoothly connected. Okay, it is smoothly connected. So overall, differentiable at x equals to 0. So it's all good. Okay, same y value, same gradient at the same point. Yep, all good. Okay, differentiable at that point. Because the derivative is 2 here. Both functions give you 2. Then the differentiability must be 2 at that point. So I will say f dash x equals to 2x plus 2 and 2 for x greater equals to 0 and for x less than 0. You can take the same domain, okay, because it's differentiable at both points. So just take the domain. So if I'm sketching this point, sketching this f dash x graph, let's sketch the left hand side. Left hand side is 2. And right hand side is when x equals to 0, it is 2. It must be the same point at 0. And then I'll say when is 1, that could be 4. Okay, it's this point here. It's this graph here. So that's the derivative graph. Okay, that point is 0, 2. Well, better label another one, negative 1, 2, and that's 1, 4. Yeah, I'm just sketching that hybrid function. Just sketching that hybrid function. One linear and one horizontal line. Okay, give you like 30 seconds to read through example 4. I'm going to read through example 4. Can you tell me what example 4, like what's the 0, 4, negative 5, what they are? Like what's the 0? What's the 4? What's the negative 5? Why there's 3 numbers? What is 0? What's the special thing about the 0? Yeah, the connection points. Okay, 0 is where they connected. What's negative 4, negative 5 and 4? What is called? Endpoints. Okay, it's the endpoints. So you know that there's definitely no derivative at those 2 points. Okay, so it doesn't matter include 4 or exclude 5. It's just no derivatives at those 2 points. And the only thing you need to test is 0 again. It's still the 0 point. Okay, still 0 point. So I will say f1x is x squared plus 2x plus 1. f2x is x plus 1. f1 dash x is 2x plus 2. f2 dash x is 1 because it's the linear. Therefore, I need to test the connection point, not the endpoints. I don't care the endpoints because there's no derivative at all. So f1 0 is 1. f2 0 is 1 as well. So it's continuous at x equals to 0. Then I will say f dash 1 0, that's 2. But f dash 2 0 is just 1. So it's not smoothly connected. It's not smooth. So therefore, the conclusion I will make is not differentiable at x equals to 0. The derivatives are not the same. One give you 2, one give you 1. No, they're not the same. I don't know which one to take. So derivative does not exist. Okay, derivative does not exist. And then I will say f dash x equals to 2x plus 2. Okay, the derivative domain is 0 to 4 exclusive. Okay, exclusive. And 1. Negative 5 to 0 exclusive. Because I can't have derivative at 0. I can't have derivative at those 2 endpoints. So it's exclusive all of those points. Okay, it's exclusive. Is here. 10 is here, but that's open circle. 0 is here, then 2 is here. Open circle as well. That's here to here. Negative 5. Negative 5 is here. Negative 5, 1. 1 will be here. 1 will be here. So 0 to negative 5 is this line here. That's the derivative function. Okay, that's the derivative function. So I will have negative 5, 1. That's open circle 0, 1. That's open circle 0, 2. Open circle 4, 10. Open circle as well. Okay, that's the derivative function. You will be asked to sketch the derivative function, and that's how you sketch it. That's where you need to have open circle, you need to label them. Questions? Okay, 3 different examples shows you end points is not differentiable, sharp points is not differentiable. Well, if a point is smoothly connected, it is differentiable, like example 2, and this one gives you is connected but it's not smoothly connected and it's not differentiable. Okay, so 3 different cases. Alright, have a look at example 5. Okay, this one is a complex question because you have 3 functions connected here, okay? f1x, f2x, and f3x. But the thing is, you know that it's joined smoothly for all of these points. Well, you know that already. Okay, so for the first one, I will say f1x is ax squared plus bx plus 9. f2x equals to a third x minus 3 squared. And f3x equals to cx plus d. Okay, can you just write me what is the derivative for the individual of them? Okay, just find the derivative for individual. Okay, for the middle one, you can't directly derive it. You need to expand it first and then derive. Okay, expand first and then derive. Don't forget that. Finished? Finished? Yep. Okay, so can you tell me which point is the connection point between f1 and f2? 3 at 3, so those two is at x equals to 3. How about the second one and the third one? 4. How about the first one and third one? No, okay, it's not connected. It's 1 connected by 2, 2 connected by 3, it's like that, okay? So now I want to find A, B, C, D values if I know that the graph is joined smoothly. Okay, if you know the graph is joined smoothly, what you will know? You will definitely know that f1,3 must be equals to f2,3. It needs to join first. f2,4 must be equals to f3,4. They're not done yet. That's just connected. Okay, that's just for connection. And you have smoothly connected. So f-1 at 3 must be equals to f-2 3. f-2 4 equals to f-3 4. Okay, so the derivative between the first one and second one, they have at point 3, they're connected and they have the same gradient. And those two functions connect at 4, they have connected and they have the same point. Okay, so that's the reason why we have this equation here. Okay, everyone understand why we have it here? Okay, so I need to expand it. Okay, I need to expand it. So for the first one, f1,3. So we have 9a plus 3b plus 9. That's F1 3, right? 9a plus 3b plus 9 equals to, you put 3 into function 2, that is a 0. Well, I can change that into 3a plus b plus 1 equals to 0. Or I will say even that's equals to negative 1. Okay, 3a plus b. That's negative 1. Just divide by 3 on everything and move the negative 1 to the other side. The second one, F2 4 equals to F3 4. Well, I'll do this two first. I'll do those two first. So F dash 1 3. What's F dash 1 3? That's 6a plus b equals to 0. Okay, F dash 1 3. Put here, that's 6a plus b, 6a plus b. And F dash 2 3, put 3 here, that's 2 minus 2, 0. Okay, 0. So F2 4 equals to F3 4. You put 4 in. F2 4, that's a 1, so a third, equals to F3 4. Okay, put 4 into that. That's 4c plus d. Okay, and the last one, F2-4. Okay, F2-4. That's okay. Dash is here. Okay, F2-4. You put here. Okay, put here. So 8 over 3 minus 2 equals to F-3 4. That's just a C. Okay, that's just a C. Yes? You have plus 9. The 9 is divided by 3. Yes. Yeah, that's a 3. Yes. Minus 3. Okay, let's name them 1, 2, 3, and 4. Okay, from function 4, you directly know that C equals to 2 on 3. Wait, 3, 6. 6 on 3. 8 minus 6, yeah, 2 on 3. C is 2 on 3. Then from number 3, you know D equals to a third minus 4 times C. So 4 times that. 1 minus 8. D is minus 7 on 3.